Hello and welcome to this video on non-linear motion, which is part of the Forces of Motion module in OCR A-Level Physics. So in today's lesson, if we are being successful and we've learnt in today's lesson, we should be able to understand the concept of drag for a body undergoing motion, be able to detail the motion of objects in the presence of drag, and finally we should be able to describe the concept of terminal velocity. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification: motion with non-uniform acceleration. So when an object moves through a fluid, it will experience a drag force from the fluid. Now drag is a frictional force that opposes the motion of the object. Now the drag force experienced by an object moving in the air is called air resistance. Now the drag force is linked to the force required to move the particles of the fluid, such as air, out of the path of the object every second. Now the lower the drag force, the higher the top speed of our object. The lower the drag force, the lower the amount of fuel used on a journey if that object is powered by an engine. Now it's important to note that drag forces can never speed things up or start something moving, but drag forces do convert kinetic energy stores into thermal energy. Now the size of the drag force depends on different factors, such as the speed of the object, the shape of the object, the density of the fluid, and the texture of the object. Now the most important factors are the cross-sectional area of the object and the speed of the object, where the larger the surface area of the object, the larger the drag force it experiences. And the faster an object moves, the greater the drag force the object experiences. Now our drag force is directly proportional to the speed of the object squared. So when the speed of an object is doubled, for example, the drag force increases by a factor of 4. Now the size of the drag force experienced by an object determines whether an object is accelerating or not. Now a velocity time graph can be used to work out if an object is accelerating by looking at the gradient of the graph. So here we have an example of a velocity time graph, with one area showing a straight line and the other area showing a flat line. Now this allows you to determine if an object has a resultant force acting on it. So you'll see with our straight line we have a constant gradient, and with a flat line we have no gradient. Now we remember that the gradient of a velocity time graph is the acceleration of the object. So our first section shows constant acceleration, and our second section shows no acceleration. Now only a resultant force acting on an object can cause an object to accelerate. So we know in our first section of our graph we have a resultant force. In our second section of the graph there is no resultant force. So let's now consider the velocity time graph of an object that is falling in a fluid. Now an object falling through a fluid, a liquid or a gas, initially accelerates due to the force of gravity. Eventually the resultant force will be zero and the object will move with a constant velocity. So if a falling object has no acceleration, it has reached its maximum velocity, and we call this terminal velocity. So let's look at this in a bit more detail. There are 3 stages to any falling object's journey. The first stage is when an object first falls. Weight is larger than air resistance, there's a resultant force downwards, so it accelerates downwards. So at the instant an object starts to fall, there is no drag force on the object, so therefore the total force of the object is equal to the weight. So the acceleration of our object is g, the acceleration of free fall. Now when the object then moves through the fluid, a frictional force drags on it. These drag forces always act in the opposite direction to an object's movement. These drag forces increase with the object's speed. Remember, the greater the speed, the greater the frictional force. And these drag forces depend on the shape and size of the object. It's important to note that streamlining an object reduces the drag force it experiences. So you can see here that our resultant force is linked to both the weight acting downwards and the air resistance against the motion. Now a resultant force causes an acceleration in the direction of the resultant force, which is Newton's first law of motion. So here in this example the object accelerates downwards as there's a resultant force acting downwards, which we can see here that the air resistance or the drag is a lot less than weight, so therefore we will have our resultant force. Now the effect of gravity, which produces this weight, produces an acceleration, like we said, of 9.81 meters per second squared. and the effect of gravity, which produces the weight, stays constant throughout the process. So if an object accelerates only due to the force of weight, we do say it is falling freely. However, the object will always accelerate at a slower rate than this, since the acceleration is directly proportional to the resultant force. The resultant force is smaller than the weight due to the effect of air resistance acting against this motive force. So we can see with our velocity time graph we have our straight line in our first section. So here we've got a constant positive gradient and we've got a constant acceleration. This leads on to stage 2, because as the object increases in velocity, the air resistance increases as more air particles are pushed out of the way per second. This decreases the resultant force and the acceleration, as shown in this particular diagram. So as we can see here, our air resistance is now a lot larger, so our resultant force is going to be a lot smaller. So the object is still accelerating, but at a slower rate. The resultant force and the acceleration it causes for the object are directly proportional for an object with constant mass, which is Newton's second law of motion. So as the resultant force decreases, the acceleration it produces decreases. So the object is still accelerating, is still getting faster, but at a slower rate. So you observe this in our velocity time graph, with a curving line downwards. Because the gradient of the line is decreasing, the acceleration is decreasing, but the velocity is still increasing but at a slower rate. This leads on to stage 3. Eventually the air resistance is the same size as the weight, so the velocity of the object stays the same, and this is our terminal velocity. So as you can see in this diagram. So now air resistance and weight are the same size, there is no resultant force, our object is not accelerating. When there is no resultant force on an object, the object has no acceleration. The object maintains the same speed with the same direction. So if the object is already moving, it will keep moving. The object maintains a constant velocity. The object has inertia. At terminal velocity, the potential energy of an object is transferred as it falls to the internal energy of the fluid via the drag force. The terminal velocity of a falling object, as we said, depends on its shape and area. So the accelerating force acting on all falling objects is weight, and would make them fall all at the same rate if it was not for this air resistance. So we can see this on the following section of our velocity time graph. The flat line has a line of gradient 0, so it has no acceleration. It has a constant velocity, which is not 0, so we say it has a terminal velocity. So when an object falls, our weight stays constant, but the resistive force of air resistance changes in size at different parts of the journey. So remember, we have our 3 stages of when an object first falls, weight is larger than air resistance. So there's a resultant force downwards, so it accelerates downwards. But as the object increases in velocity, the air resistance increases as more air particles are pushed out the way per second. This decreases the resultant force and acceleration. Eventually, the air resistance is the same size as the weight, so the velocity of the object stays the same. This is terminal velocity. So we can see this in our 3 stages of our velocity time graph. So in our first stage, we know that force is equal to mg, so acceleration is going to be equal to g. In our second stage, F is equal to mg minus d, so A is equal to mg minus d over m. And in our third stage, the force is equal to 0 and our acceleration is equal to 0. Now if the object was falling through a liquid instead of air, the resistive force generated by a liquid is larger, as the particles are more densely packed compared to air. So this means a falling object reaches stage 3 faster. Now if the object was falling through a liquid instead of air, the resistive force generated would be larger, so this means that the falling object would need to fall much further through the air compared to water to reach terminal velocity. So on the moon, where there's little atmosphere, all objects will hit the ground together. But on the Earth, air resistance causes things to fall at different speeds, and the terminal velocity of any object is determined by its drag in comparison to its weight. So the frictional force depends on the object's shape and the object's area. Now we can determine the terminal velocity of an object falling in a fluid. A ball can be dropped in a tube of cooking oil, and the ball will fall through the oil down to the bottom of the tube. So you'll see we have our fluid resistance acting against motion and our weight acting downwards. So the object is dropped through a fluid, and the object is timed as it falls through the fluid with a stopwatch. The time is recorded at marked distance intervals in the fluid, and then the distance travelled and the time taken measured are used to determine the velocity of the object at different parts of the fluid. The velocity of the object, including the terminal velocity, is then determined for the journey. Now the object will maintain this terminal velocity until it hits the bottom of the cylinder. Now throughout the journey, the weight acting on the object stays constant, but the resistance it experiences changes. Now if there was no fluid, the object fell in a vacuum, there will be no resistance, so the object will constantly accelerate down due to weight. Now it is very difficult to measure the terminal velocity of an object, so this experiment would get inaccurate results. So it's very difficult to measure when the object would have actually obtained terminal velocity, as it's difficult to measure the timings of an object falling as it occurs very quickly. To solve this, you can use computer sensors and light gates, as this would reduce your uncertainty in your time and measurements, as it would mean that the random error produced will be smaller. Now it is also unlikely in any class experiment that the object would have achieved terminal velocity, as it takes a relatively long time of falling to achieve terminal velocity. So to solve this, you would have to increase the height at which the object falls in a fluid. Now all objects when falling in a fluid for long enough time will achieve terminal velocity. The fluid could be oil, could be water, could be air, but it's important to note that the denser the fluid, the greater the drag force generated, the faster the object will reach terminal velocity. So to summarise what we've looked at in today's lesson, we've looked at the drag as the frictional force experienced by an object travelling through a fluid, the factors affecting drag for an object travelling through the air, and the motion of objects falling in a uniform gravitational field in the presence of drag. We've looked at terminal velocity and the techniques and procedures used to determine terminal velocity in fluids. So if we've been successful and we've learnt in today's lesson, we should be able to understand the concept of drag for a body undergoing motion, detail the motion of objects in the presence of drag, and describe the concept of terminal velocity. So thank you for watching this lesson on nonlinear motion, which is part of the Forces of Motion module in OCR A-Level Physics. Thank you so much and have a lovely day.